So, welcome back, students, and we have completed with our first part, that is the population mean. We were testing that any sample taken out from the population, and we are claiming some value, whether that is equal to population mean, greater than or less than population mean or not. Okay, that is what we have tested in the above two examples. Now we will be taking the difference of two population means. Okay, this may also be a case. So in previous section we have learned about the testing of hypothesis about the population mean already. Okay, and but there are so many situations where we want to test the hypothesis about the difference of two population means. Okay, isn't it? That is, we want to see that is there any difference between the two populations. Okay, so for example, say for example, this two manufacturing companies of bulb produce the same type of bulb, and one may be interested to test that one is better than the other or not. So any investigator may be want to test the equality of average incomes of people living in two different cities. Okay, whether the average income in this Delhi city is equivalent to average income in the Bombay or not. Okay, so therefore we require an appropriate test for testing the hypothesis about the difference of the two population means. Okay, now we will be testing our hypothesis about the, instead of population mean, we will be testing our hypothesis about the difference of two populations. Okay, so let be the two populations, say population 1 and population 2 under study, and this mu1 mu2, this mu1 is the population mean of population 1, this is the population mean of population 2, this is the standard deviation of the population 1, standard deviation of the population 2, denotes the mean and this variances. Okay, denotes the means and the variances of population 1 and population 2 respectively. Okay, where both this mu1 and mu2 are unknown, that is, we do not know the population mean, these two, but their variances of these population may be known or may not be known, unknown, may be known or may be unknown. Okay, so now we will consider all possible cases here. So for testing a hypothesis about the difference of two population mean, we draw a random sample of large size, say n1 from population 1, and take a random sample n2 from population 2. Okay, so say for example, this is the population 1, this is the population 2. So we will take a sample of n1 from it and take a sample of n2 from it, such that this n1 and n2 both are greater than 30. Okay, so these two population may or may not be normal, but according to central limit theorem, the sampling distribution of difference of two large sample means asymptotically normally distributed with mean. So the mean of this difference will be equal to mu1 minus mu2. This will be your mean of the normal distribution, and what will be your this variance, and your variance will be equal to sigma 1 square upon n1 plus sigma 2 square upon n. So this will be the variance of the two, difference of the two population means. So now follow the same procedure, we will following the same procedure as we have discussed in the previous section, keeping in mind these two things. Okay, so first of all, we will set up a null hypothesis and then alternative hypothesis. So here we want to test the hypothesis about the difference of the two population mean. So we can take the null hypothesis as that the mean of the population 1 is equal to the mean of the population 2, that is no difference in means. Okay, or this mu1 minus mu2 is equal to 0, that is difference in two means is 0, and then what will be your alternative hypothesis, that the population mean of population 1 is not equal to population 2. So there may be one tailed, that is this population 1 is either less than or equal to population 2. Its alternative complement will be that population mean of first population is greater than population 2. Similarly, the null hypothesis, another right tail, that mu1 is greater than or equal to mu2, and your alternative will become that mu1 is less than mu2. So in this case, for testing the null hypothesis, the Z statistics is given by this sample mean. Say for example, x bar is the sample mean of from the first population. That is, we have drawn these n1 samples now. So it has a mean of x bar, it has a mean of y bar. So your Z will be equal to x bar minus y bar minus mu1 minus mu2 divided by standard error of x bar minus y bar. Okay, and which will be equal to, this will be equal to x bar minus y bar minus mu1 minus mu2 and square root of sigma 1 square upon n1 plus sigma 2 square upon n2. As in the null hypothesis, we are saying that our mu1 is equal to mu2, and if our mu1 is equal to mu2, so this value, this mu1 minus mu2 should be equal to 0. So we will assume here that your Z will be equal to x bar minus y bar divided by square root of sigma 1 square upon n1 plus sigma 2 square upon. Okay, so this will be our Z. So now the sampling distribution of test statistics will depend upon what? The variance of first population and variance of second population. They may be known or may be unknown. So what will be the first case? Say for example, that both are known and are equal, these variances. So if they are equal, your formula will become like this. That is, this will be also sigma, this will be sigma. So sigma, your sigma square, this will be sigma square. So sigma will come out and this formula will become like this. Second case may be, they may be known, but sigma 1 is not equal to sigma 2. So your formula will remain same, what we have derived above, this one. Okay. So this will remain the same. Third may be that they may be unknown but are equal. So in that case, the sigma square is estimated by the pooled sample variance. Okay. And what is that pooled sample variance? That is, from population 1 we have taken n1, from population n2 minus 2, because 2 population. That is n1 minus 1 plus n2 minus 1. So it will become n1 plus n2 minus 2. And this will be n1 into s1 square plus n2 into s2 square. So how we can find this S1? These can be find like this. This is the formula for S2. This is the formula. Okay. So here your degrees of freedom will be N1 plus N2 minus 2. Okay. Now what can be the fourth case? Right. So this your pooled sample variance will come out here and your formula will become this one. Other case may be that these things are unknown and these are not equal. So in that case, these sigma square value will be replaced by the sample variance of first population and sample variance for the second population, and your formula will become this. Okay. So now let us do some examples about this thing. So in two samples of women from Punjab and Tamil Nadu, the mean height of 1000 and 2000 women are 67.6 and 68.0 inches respectively. So we have taken 1000, that is your N1 is equal to 1000 from Punjab, and your this mu1 is equal to 67.6. Then we have taken 2000 women from your Tamil Nadu, and your height, population height, sample height is 68.0. Okay. So So if population standard deviation for Punjab and Tamil Nadu is this, it means your sigma 1 is equal to sigma 2 is equal to sigma is equal to 5.5 standard deviation. Okay, so standard deviation for both the population is same. Okay, so can the mean height of Punjab and Tamil Nadu women be regarded as same at 1% level of significance? So these are the sample values. Now we have to make an inference about the whole of the population. Okay, and we have the this standard deviation for whole of the population, which is equal to 5.5. So now here we want to we wish that the to test that the mean height of Punjab and Tamil Nadu women is same. Okay, so what will be our claim will be that this mu1 is equal to mu2. So because there is equality sign, so this will be your null hypothesis, and its complement will be that the mean height of this population is not same. So this will be your alternative hypothesis. Okay, so now we will be putting these values in your formula. So our formula will be fitted here, that is sigma is known and both are equal. So your this z statistics will be equal to x bar minus y bar upon this sigma into 1 upon n of this. So when we put these values, so our z statistics came out to be minus 1.88. Okay, whatever value of z came out to be minus 1.88, right? So the critical value, tabulated value for this 1% level of significance, because it is a two-tail test, okay, it is 2.58. Okay, so if you see, this is the 2.58, this is the plus 2.58, and your minus 1.88 lies in the acceptance region. So we will accept the null hypothesis. Hence the mean height of a Punjab woman and that of the Tamil Nadu woman are same with 99% confidence interval. Okay, because the difference lies in between these acceptance, the mean difference between these two. Okay, difference is not significant, it is not outside the acceptance. Okay, so this is how we do. Now we will be doing quickly one more thing, and that is about the population proportion. I will put some new pages. Okay, so now we will look up with the population proportion. So we have discussed the procedure for testing of hypothesis for population mean up till now, isn't it? Okay, so when sample size is large, but many real world situations in business and other area where collected data are in the form of counts. Okay, is in the form of counts, or the collected data are classified into categories or groups according to the attribute. Okay, so instead of a continuous data, we have a discontinuous data. So for example, people living in a colony may be divided into two groups, male and female, with respect to the characteristic of sex or gender. The patient in a hospital may be classified into two groups as cancer and non-cancer patients. Okay, so these can be the two categories. Okay, and the lot of articles may be classified as defective and non-defective. Okay, so similarly this range is very high, that you can define into two lots based on their attributes. So here collected data are available in dichotomous or binary outcomes. Okay, so you have this so this Shreya is asking that if the value do not lie in acceptance region, then what we will do? So if your value do not lie in acceptance region, then we reject the null hypothesis and accepts the alternative hypothesis. So what was our null hypothesis? Our null hypothesis is that the mean height of a woman of Punjab is equal to woman of Tamil Nadu. We conducted the test, found that our calculated value lies in the acceptance region. Hence, our null hypothesis is accepted that the mean height of a Punjab woman is equal to the mean height of the Tamil Nadu woman. If it is not true, if this value does not comes in the acceptance region, then we will reject the null hypothesis and accept the alternative hypothesis. That is, we say that the mean height of the Punjab woman is not equal to the that of the Tamil Nadu. Okay, so this is how we do. So I think now the this question of Shreya Mishra is clear. Okay. So, for example, we were here. The characteristic sex can be measured as success if male and failure as female or vice versa. So, in such situation, proportion is actually a suitable measure. Instead of mean, what we do in such cases, we go for the proportion. So in such situation, we require a test for testing the hypothesis about population proportion. Okay, we test the hypothesis about a population proportion. So for this purpose, let x1, x2, xn be the random samples of sizes and taken from a population with population proportion p. Okay, the population proportion is p, right? Also let x denote the number of observation or element possesses in certain attribute out of the n observation of the sample. Then sample proportion p can be defined as, so if there are n individuals we have taken, and out of those the requisite attribute is exhibited by x individuals. So what will be your p value? It will be equal to x by n, and it is always equal to or less than 1. Okay, when sample size is sufficiently large such that if we multiply this np and it is greater than 5, okay, and similarly your nq is also greater than 5, okay, then by central limit theorem your expectation of p is equal to p. Okay, sorry, it is capital P, that is of population proportion, and variance of this your p will be equal to, again this will be population proportion, that is pq upon pq upon n, where this p is equal to 1 minus q, and this will be PQ. Standard error will be square root of PQ upon N. So now again we will be following the same methodology. So if we take equality sign, that is the sample proportion is equal to the population proportion. Okay. In that case, this is the null hypothesis, and opposite of it, inequality sign, it is the alternative hypothesis. For one tail test, this will be P will be less than or equal to P naught, and this for this it will be greater than or equal to P naught. So our Z statistics will be given by P minus EP upon SEP, and this will be P minus P naught, where P naught is the population, this, and this will be square root of P naught Q naught upon N. Okay, which I have written here is as capital P. So here it is P naught. Okay, so after that we calculate the value of test statistics and compare it with the critical value as given in table 1 in the starting. So let us understand this with an example. Say for example, a machine produces large number of items out of which 25% are found to be defective. To check this, company manager takes a random sample of 100 items and find 35 items defective. So is there an evidence of more deterioration of quality at 5% level of significance? Okay. So the company manager want to check that his machine produces 25% defective item. And here the attribute under study is defectiveness. And we define our success and failure as getting a defective or a non-defective item. Okay. So our population proportion, this P naught, capital P naught, is equal to 0.25, isn't it? Defective items. Whereas our observed or sample proportion is equal to 0.35, that is 35 out of 100. Okay. So here we want to test that the machine produces more defective item, that is the proportion of defective item greater than 0.25. So our claim, so what will be our claim? P greater than 0.25. Okay. If we want to change that machine, so we have to prove that our this P should be greater than 0.25 at this 5% level of significance. Okay. And other its complement will be that this P is either less than or equal to 0.25. Because there is a equality sign, so this will constitute our null hypothesis, and this will constitute our alternative hypothesis. Now we will be applying our Z statistics, where our Z statistics will be. But before applying the Z statistics, we will see that our NP and NQ are greater than 5 or not. So here it will be 100 into 0.35 is equal to 35, which is greater than 5. Okay. So we can very well apply your this Z statistics. So here this 100, this P, we have used this P, small p. So into 1 minus 0.35 is 0.65, so equal to 65, which is greater than 5. Okay, hence it has satisfied our condition for normality, and therefore we can apply the Z statistics, where this Z statistics is given by P minus P naught upon square root of P naught Q naught upon N. So we will put all the values and it comes out to be 2.3. So now we will see that whether this lies between your this two-tail test. For two-tail test at 5% level of significance, this Z it will be equal to 1.645. Okay, so this 1.645, okay, no, sorry, one tail test, this is a one tail test. Okay, and it will be right tail test. Why? Because we are testing for this thing, that is it should be less than or equal to 0.25. So our 2.31 is far ahead of 1.645 critical value. So this 2.31 lies in the rejection region. So our null hypothesis is rejected and our alternative hypothesis is accepted. Okay. So what was our alternative hypothesis? That the proportion of defective items are greater than 25%, which is the claim of that particular machine at 5% level of significance. Therefore, we need to change that machine. Okay. So this is how we can conduct the test. Okay. So it has been observed. Now our last topic, okay, is difference of two population proportion. Okay. So now instead of one population, we will be using two populations. Okay. And when we will be using two population, so first proportion will be, say for example, this is the proportion for first population. So it will be equal to x1 are the success attribute from n1 samples. And for population 2, x2 are the success attribute out of n2 population. Again, this should follow that np1, n1q1, n2p2 and n2q2 should be greater than 5. Then we can apply the central limit theorem, and this will follow this sampling distribution will follow approximately normally. Okay, and its mean will be equal to the mean of this proportion, that is P1 minus P2, that is we are testing for differences of two population, will be equal to proportion 1 minus proportion 2, and that of variance of P1 minus P2 will be equal to P1 Q1 upon N1 plus P2 Q2 upon N2. Okay. So similarly, we can find out the standard error by square root of this variance of difference. So now we can apply the this hypothesis for two-tailed test. This proportion of first population should be equal to the proportion in the second population, and alternative hypothesis will be that these proportions are not same. For one-tailed, again, instead of this mean, we will be using this population proportions, and this will be your formula. Okay, and because as a null hypothesis, we are saying that this proportion 1 of first population is equal to the proportion of success in the second population. So this will be equal to 0. So our Z statistics will be like this. Okay. So now generally these proportions are being calculated from the pooled value, when this proportion are not known from the original population. So this pooled proportion is equal to N1 P1. P1 is the first sample proportion, second sample proportion upon N1 plus N2. So it is N1 P1 is nothing but X1, and this N2 P2 is nothing but X2. So this will be equal to X1. This is pooled proportion is equal to X1 plus x2 upon n1 plus n2. Okay, and once we know this pooled proportion p, so q can be calculated 1 minus p bar. So it will be equal to this, whatever this p value you will get, so subtract this from 1, so you will be getting q. So now let us do this question. So in a random sample of 100 persons from a town A, 60 are found to be high consumer of wheat. In another sample of 80% from town B, 40 are found to be high consumer of wheat. So, do these data reveal a significant difference between the proportion of high wheat consumers in town A and town B at alpha is equal to 5% level? So, what we are having is that in this question we are having this N1 is equal to 100, N2 is equal to 80. Okay, now your x1 is equal to 60 and your x2 is equal to 40. Okay, 40. So from here you can calculate that your p1 will be equal to 0.6 and your p2 will be equal to 0.5. Okay, so what will be our null hypothesis? That proportion 1 is equal to proportion 2, and our claim that they are not equal complement inequality sign is our alternative hypothesis. So now we will test them whether these will follow a normal distribution. Yes, we have seen here that this 60 is greater than 5, 40 is greater than 5, 40 is greater than 5, 40 is greater than 5. So they follow the normality. Okay. So now we will be calculating the your pooled proportion. So your pooled proportion from the above formula, this n1 p1 n2 p2 upon this, or x1 plus x2 upon n1 plus n2, this came out to be 5 by 9, and from here q will be 1 minus p will be 4 by 9. So this z statistics we have already have this formula. So when we put this value, these came out to be 1.34, and this critical value at 5% level of significance are from minus 1.96 to plus 1.96. So what we see is that this our 1.34 lies in the acceptance region, and when it lies in the acceptance region, we accept our null hypothesis, which includes the equality sign. Okay, so the proportion of wheat consumer in town A and town B are same at 5% level of significance. Okay. So basically this completes our Z test, and in this unit what we have covered is that how to judge a given situation whether we should go for a large sample test or not, applying the Z test for testing the hypothesis about the population mean and difference of two population mean, and applying the Z test for testing the hypothesis about the population proportion and difference of the two population proportions. So this completes our Z test. Although there is one more thing is there, you can also test the difference in the variance or the population variance also, but that will become more advanced and is out of your syllabus. Not out of your syllabus, but it is not required at your level of your BVSC and AH. So we will not be touching that in this lecture. So we will be dealing with the population mean and this population proportion and the difference between the population mean and difference between the population proportion. So this is all from my side, and there was only one doubt was there from Shreya Mishra, which I think I have cleared. So this is all for today, and thank you very much for being with me in this lecture. And tomorrow we will be starting with the T test. Okay. So thank you very much.